So today we begin the Spring 2021 lecture series. This is the 7th semester. Upon its completion, we will have seen 28 assorted presentations, all related to the built environment. So today we begin this series of 4, and we have BCT's own Professor Ben Weil. Professor Weil's topic would be as relevant as any of the topics covered in this series thus far, as it'll address COVID-19 transmission and draw on the lessons Professor Weil has learned in consulting with building owners, operators, constructors, and renovators, all working to operate their buildings safely and profitably within the context of the pandemic. Not an easy task. The presentation will supply some discussions of these protocols while considering the evolving understanding of the virus and supply some guidance in thinking through the best practices to minimize risk in both residential and commercial settings. Finally, never moving far away from his concern with the amount of energy our buildings consume and their impact on climate, Professor Weil will speak to how immediate intervention investments addressing COVID can pay off in the long term by saving energy while supplying healthier, more comfortable, more productive, and safer indoor environments. So I am very, very pleased to present my friend and colleague, Professor Weil, whose ability to dissect complex building physics issues and mechanical complexities into teachable bites of extraordinarily useful solutions never ceases to amaze me. So please welcome Professor Ben Weil.
Wow, you could keep going, Carl, if you want. I don't know if I can live up to that. So Carl asked me to do this presentation based on a similar presentation that I gave last year, when I think our sense of hopefulness was a lot lower than it might be now. I mean, now we have these vaccines coming along. We have a federal plan. So I think that to some degree, this context is like, really, we're going to talk about COVID. I'm sure everybody is really excited to talk more about COVID. So I'm going to try to relate this talk to a lot of general principles about indoor air quality and energy efficiency and kind of building maintenance and building operation, so that I hope that a lot of this will translate to what I hope is by next year a post-COVID world when we can start to think about other things and operate differently. So if you give me a second here, I'm going to share my presentation. Okay. So there's your title. And so what I'm going to talk about today is first just these concepts about reducing respiratory virus infection and spread, and then some of how these things relate to a bunch of other things. We'll talk about some applications, right? There are so many different kinds of buildings, so many different activities people do in buildings. So we're not going to be able to cover everything. And I tried to focus with these on applications that I think most of the people who are here will have some way of relating to. So we'll have a little bit about homes, but mostly our homes are actually our safe spaces where we're living with people, and either they have it and we soon will, or they don't have it and we prevent ourselves from doing it. But if we look at schools, and particularly as we try to do work, and because we're kind of building and construction oriented, I want to focus on the job site use, and the idea that with the right controls, people can be working cheek by jowl in construction environments and not spread the disease. And then I want to discuss some opportunities for the post-pandemic period. And I hope that will be something where we actually can have it evolve into an actual discussion and less of a lecture. So the areas that we're going to apply is multifamily residential, because that's where we've got a really interesting problem. Job site, both new construction and renovations, looking at how meeting rooms, when we do have to get together people in rooms, how we can operate this safely, and kind of the subject of most concern of getting our people back into classrooms. So I know for certain that none of this is new to anybody, right? We've all been living with this for long enough. Although you may remember back in March, April, May, June, those of us, and I would count myself and Carl in the general HVAC crowd, who were saying, it's aerosolized transmission. Air is going to matter. Surfaces matter less. It may seem that everybody knows that now, but if you think back to the late spring, people were not certain about that, and it was a real fight to get people to start thinking about air contamination and ventilation and the importance of masks, right? And now, obviously, we're continuing to try to get people to understand the importance of masks. So these approaches to avoiding COVID spread also fit kind of how we think about contaminations in general, right? So our first approach is to avoid, right? If we can just not gather, if we cannot put ourselves in large groups, we avoid the potential for spread. If we have to get anywhere near each other, we put on a mask, not news. A mask, if you ask me, is a filter, right? So really this filtration thing that I put way at the bottom of this pyramid, or this upside down pyramid, because the most important measure, right, is avoiding. The next one is wearing masks. The next one after that is distance. So these are ranked in order of effectiveness. After that, we really need to start ventilating spaces. And that's why outdoors is so good, right? That's why if we can gather outdoors, we have lots of air exchanges around the people who are gathering. Then we want to filter. And then the last thing, it's not nothing, is to clean surfaces. And we could even consider cleaning the air. These are the same steps that we take for risk reduction for other indoor air quality issues, right? We start out with source reduction, then we focus on source spot ventilation. We want to evacuate fumes, we want to evacuate contaminants. Then we do general ventilation to turn the air over. And finally, we'll use filtration and air cleaning. So during this period, then we're talking about the things that we just did, and then we can look at how we can use those, use energy efficiency techniques to make those things work for us. So the biggest thing is, if we're going to be doing more ventilation, we should try and recover the energy that we would otherwise lose on that stale air. So that's going to have a large impact on our energy efficiency. Scheduling and programming. So that's, can we shut buildings down? Can we time when people are going to go into buildings such that we don't have to have as much of the building open, and therefore not heating and cooling it and lighting it and so forth. And then if we can personalize comfort, and so that could be as much as personalizing spaces, right, where we create those shields, face shields and plexiglass shields in certain spaces, and people are doing that with like desks in schools and so forth, to personalizing comfort. If we can have a space heater near a person, we can get that person's comfort up at a higher level. And you'll see in a little bit why that helps us deal with this higher air turnover that we're talking about. And finally, we want to reduce the difference in pressure, or reduce the pressure drops that we get in the ducted systems that we're dealing with. And we'll see in a minute why these ducted systems are so important, and why reducing pressure drops has a big impact on both energy and effectiveness of the filtration and air exchange systems that we're trying to operate. And you can see how these two systems kind of come together, right? Avoidance, masking, and distance are all kind of related to personalizing and compartmentalizing. If we can make those systems work together, that's great. And then distance in particular is going to work with scheduling. If we need to space more people out, we need to schedule people's times in buildings a little differently. And then with ventilation, we want to do heat recovery. And finally, if we can use a low delta P, if we can reduce pressure drops, then our filters will be more effective, our air cleaners will be more effective, and we'll have heating and cooling systems that actually work. So the main thing to point out is that the concepts that we use in trying to reduce the pollution, which is a virus, are the same concepts that we use for reducing all types of other pollution. And this is the page for Germans. So Alex, if you would care to read the quote from Parcelus for us? No, nothing?
Well, okay, if you want me to. You sure you want me to?
Yeah.
Alle Dinge sind Gift und nichts ist ohne Gift. Allein die Dosis macht, dass ein Ding kein Gift ist. Okay.
Yeah. See,
There you go.
see, I didn't want to do that myself. That's also known as the dose makes the poison. And it's the same thing with COVID, right? We know that if we have very, very few particles containing virus that we inhale, we're very unlikely to get COVID compared to if we inhale a very large dose of COVID, coronavirus. And also the severity of the infection, the severity of our reaction to it, obviously mitigated by age and prior conditions and all those sorts of things we all know about. That dose is what goes from having a mild case or a case that's asymptomatic to or not catching it, to fighting it off before you ever actually get it, getting a chance to build those antibodies. It's all about the dose. So if we can reduce the amount of virus in a space, we reduce our likelihood of running into it, right? You know, if there's this little droplet running around, maybe we just don't ever get it. So that's one part of it. But the other thing is, so here this quote is about the pile of manure, but it can be for any pollution source. If you've got a pollution source, remove the pollution source. Don't try to ventilate it away, right? So that's a really important thing to think about with this virus as well, is identifying people who are contagious and removing them from the building, which is obvious, but it's got to be a first step. So let's think about what these sizes of these particles are and how they're going to affect us and how they relate to other pollution that we are already exposed to. So in particular, right, so here's the coronavirus itself at 0.1 to 0.5 microns. Fine, that's really, really small. But we're more likely to find it inside a respiratory droplet, inside an aerosolized droplet. And that's actually larger than the particle that we mostly think about with air pollution, which is the PM 2.5 or 2.5 micron dust particle. That's the thing that gets deep into our lungs, causes lung disease, heart disease. It's a major cause of early death among humans, especially as we've gotten more and more pollution. And the biggest source of that pollution is the combustion of fossil fuels, period, on the planet. But you'll see that we've got similar sizes. So whatever we do to try to filter coronavirus, we're probably going to be pretty effective on also filtering PM 2.5. So that's one thing for us to think about. And let's look at, so prior to the pandemic, what were the pollutants that really, really impacted people? I want to point out, so this is normalized into a disability adjusted life years, right? So that we can kind of normalize all of them. This is a logarithmic scale, right? So the things over here are way bigger than the things over here, right? And everybody knows that, but just that's what you're looking at. So PM 2.5 is by far the biggest impact on human health. So if we can create systems that are going to improve our indoor air quality with regard to PM 2.5 by accident, while we're trying to take care of the coronavirus, and we leave those in place, we've done ourselves a huge favor in terms of indoor air quality. But some of these other things, while less than PM 2.5, are still really important, and I want to hold on to those thoughts. So the main thing we do to deal with particles in indoor air is to filter it. And so you can use this MERV filtration rating system. So it's minimum effective reported values is what it's an acronym for. And generally speaking, you'd want to have a higher than a MERV 13 in order to get most of those really, really small particles. And, you know, getting greater than 95% is great. So here you can see this pleated filter. You can kind of add those filters and get yourself a really high filtration. So we should be upgrading from what is standard operating equipment is usually about a MERV 8. And you usually want to increase that filtration level. But let's think about this for a moment. So here's where we're putting most of our filters. We're putting them in air handling units, right? So these are just typical. Here's one in a building, actually in Natick, where I was on Friday. So I took a picture of it. And typically you have the same thing. They're going to take in some fresh air if they're designed to do that. They're going to recirculate air, and they're going to pass it over a heating and a cooling coil and a filter. And here you've got a residential furnace with an air conditioning coil in it. It's the same kind of box, just all at different scales. So let's think about what they do. They have in this particular design for a typical commercial air handling unit, you've got return air. So that's air from the building, say potentially contaminated from a lot of people coughing and breathing and doing whatever they're doing. You're going to have some portion of outdoor air, and now those two air streams are going to mix, right? Then that's going to go through a filter, and it's either going to go through a cooling coil or a heating coil or both, right? You might cool it down to dehumidify and then heat it back up to send it back as neutral air. And we can talk about whether that's a wasteful way to do things or not. And then you supply air, which is this mixed air that has gone through a filter. Lovely. In this residential furnace, here's that sort of filter. This filter is probably like a MERV 2. It's, you know, it's really bad. But, you know, so your inclination would be just pull that filter out and put in a MERV, say 13, MERV 16 filter. And then the fan will blow it past the heat exchanger from this natural gas, atmospherically vented natural gas furnace, and it'll blow it into the room, and that's what it's doing. So just when you're thinking about these units, not everybody has one or knows exactly how they work. So now you've got a kind of a picture of what's this tool that you see in American buildings. And I'm going to say American buildings in particular, because in a lot of the world, we do a whole lot more of our heating and cooling by moving water rather than air. So it's not all good news. So let's say we put in this higher MERV filter, right? This filter with a higher resistance, right? You've all experienced this. Everybody's put on a mask recently, right? And you can put on that, like the 2 pieces of cotton, the minimum mask that you're supposed to wear, and you're pretty able to breathe through it. But maybe you try running with that mask on and it feels a little hard, right? There's resistance to airflow and your lungs are having to suck a little harder. Well, I don't know if you've done this. I've recently taken to the double mask thing. So you put on the maybe you've even got yourself a KN95 mask, which is kind of equivalent to a MERV 16. You put that over your, in your mask, and then you put another mask over it. And now you're really sucking in the air. There's some resistance. It takes a little work. And in particularly if you don't have really great lung capacity and lung strength, you're feeling uncomfortable and you don't want to go for a run. Or skiing or whatever. So that's fine, but that resistance to airflow also can result in problems. So ironically, if you have a high efficiency motor that can change how hard it works depending on how much resistance there is, so the more resistance, the more pressure, it will ramp up. You actually end up increasing your energy use because you have to push harder to get that air through the filter. If you don't have that high efficiency motor, like an ECM motor or a variable frequency drive, then you actually have a comfort problem. If your motor was sized for the duct system that you have to deliver air everywhere at I don't know, half an inch of mercury as a pressure, right? And then you take up half of that by the filter. Now you don't have enough air force to deliver air to all the different places. And so whichever place is kind of the end of the duct line, or if you've got leaky ducts, it's even harder. You're actually not going to deliver the heating or cooling air where you wanted it. So you're going to get comfort problems. It can get worse though, because if you can't move air over the air conditioner coil or any cooling coil, right? If you can't move air over it, eventually it's going to start doing a really good job of dehumidifying, right? You've got this really cold coil, so you're going to condense a lot of water on it. And because the air is not moving past it, it gets colder and colder and colder, and it will eventually freeze water around the coil. And now you've got, rather than a coil, you've got a completely stopped airflow problem. This can happen. Not only that, now the refrigerant is not evaporating on that evaporator. And so now your compressor is dealing with a liquid that's circulating as a liquid with no gas separation, and so you can blow up your compressor. So there are consequences to too much delta P, right? Too much difference in pressure. You could, in a furnace, you can crack your heat exchanger. If you're not moving air over that thing to cool it off, it's going to get really, really, really hot. And eventually, if a metal gets hot enough and flexes enough, it'll crack. Once you crack your heat exchanger, you now have your combustion gases directly connected to the air that's blowing into your house. So you've now got a carbon monoxide distribution system for your house. But within reason, if you just slow the air down a little bit and you don't do any of these really catastrophic things, you just get better dehumidification because you have a little more residence time over the coils. Okay, so how do we deal with this problem? So one solution over here on the left is let's just throw a bunch of filters in. We've got a MERV 13 pleated filter, a carbon filter for odors, a UV light probably doesn't create too much resistance, and then a giant HEPA filter to make sure we're filtering everything, getting all our COVID. That's the filter we want. But you notice that all of these are taking up the entire cross-sectional area of this air handling unit. And so the pressure drop across them is going to be very large, and there's not that much surface area relative to the airflow. Over here, you have a different type of filter box, which it basically holds things in a V formation. So you've got a lot more surface area relative to the airflow. And by increasing the surface area, you increase the filtration, right? Because there's more opportunities for particles to hit or get trapped by or just simply get entrained in the filter media. Or and because there's so much more surface area, there's less of a pressure drop, right? You're not trying to squeeze the air. So the answer is large surface area diagonal filtration. And I would say where there's an opportunity, a good investment for anyone in any one of these levels of air handlers, from the giant commercial ones to that little furnace in a house, would be a filter box that allows you to install either something with really, really big pleats. We're talking about 4 inches, 5 inches, 6 inches thick HEPA filters. So big pleats, lots of surface area, or an actual diagonal filter box like this one. So those are good solutions. Okay, what about disinfection? So there's been a lot of excitement about interest in using the UV radiation to basically kill all the virus that might be circulating through the air. And we already had, prior to the pandemic, we had a number of UVC. UVC is the wavelength of UV that is the most effective, but all UV wavelengths will have some effectiveness. Putting those into air handling units as a way to actually keep the coils, which often condense moisture, their job is to condense moisture, and therefore, if there's dust on them, mold can grow, you can grow things. So decontaminating those coils was a way of improving air quality. And then the other form is the one you have up here in this room, which is high UV disinfection. So this is where the natural buoyancy of the air causes it to, if you think about how we emit particles off of ourselves, there's natural buoyancy off of us. And so that air that's rising off of us is going to have the most likely to have contaminants in it, including virus particles. That is going to go by natural convection through these slightly warm UV lamps, which are set so that we can't see them, because they would damage our eyes and skin if we could actually see if the UV rays could actually get us. This is far more effective. So the problem with UV technology in the ducts has to do with the residence time. The air is blowing by that really fast. And so a virus particle that's going in that air is not going to have a very strong likelihood of being impacted by the UVC rays for long enough to necessarily kill it off. Whereas you get lots and lots of passes on and longer residence time, because we're not moving the air as fast on these high UVC disinfection units. So if one was investing in UV, I would tend to want to look at ones that are in the room. And there's another reason that I'm going to get to in a minute. But first, I want to talk about some systems that I do not have a lot of confidence in, and I feel like are being sold pretty heavily. And I've actually had a lot of kind of heated discussions with consulting engineers for a bunch of schools who all would rather not increase the rate of air change and would instead like to install, say, bipolar needlepoint ionization or other types of ionization. And I have this up, and I'm not going to discuss it much, which is basically to say there's really no good studies. There's a huge variation in technology and effectiveness from one company to another, and there's no standard, and so there's no regulation. It's very hard to know what's a good technology and what's not. And many of them, not all, but many of them will combine to emit ozone, and ozone generation is not good for humans, well, for lots of living things to inhale. So I would say these are probably not the tools that we want to prioritize, although many of them may be promising. We just don't have the data. But I want to think about this problem. If we're talking about filters or UV radiation inside an air handler, the air handlers will circulate 80 to 90% of indoor air at full loads. but they're almost never at full loads by definition. So here's a histogram of the number of hours of heating and cooling at UMass. Now, this is not including non-weather related cooling. So we have lots of cooling that's for indoor spaces that require cooling year round. That's not these. This is just cooling that's driven by weather. So granted, there's going to be more operation of a cooling system at a big institution like UMass. But generally, you can see that most of the hours happen when the weather is just around freezing. Well, that's about half, right? That's literally about half of the capacity. We're only ever at full capacity for just a few hours per year, way down here where it's really cold. So you can't really count on enough airflow going through your air handlers to do all the filtration that you'd like it to do, or to kill all the viruses if you were putting UVC in those air handlers. And so we have return air. We also have outdoor air. And so we're always mixing that air. And that brings us to the next problem. Right? So another classic maxim of indoor air quality is the one this guy just realized, which is that the solution to pollution, at least at this scale, is dilution. And the way we do that is we bring in fresh air. So we talk about air changes per hour, right? And that's basically N, a number of air changes per hour. And the question is, are we really getting a full air replacement? When we say, I want 1 air change per hour, am I replacing all of the air? So if we designed our system to have a full displacement flow, which by the way is a great design, and all of the labs at UMass should be switched over to displacement airflow, and we'd actually save a huge amount of energy, but I'm not going to get into why that is so. Just suffice it to say it works real good. Okay, so if we really had full displacement flow, we actually could say 1 air change is going to change over 100% of the air. But that's not really what we have. Either we have injection of supply air and it's entrained, right? It's moving around and it's mixing. And in fact, we usually argue that we want good mixing. Mostly HVAC designers actually design to really mix the air well, right? We want to have comfort. We want to have fresh air mixing everywhere in the building. Lots of good reasons to get full mixing of the air. And then if we're using an air handling unit, like a commercial air handling unit, we're usually mixing fresh air and room air in different proportions depending on ventilation requirements or how cold it is outside or how hot, whatever. We're mixing them on purpose. We're really getting mixed air. So what's that really doing to our air changes? So one way to think about this is to remember that we say we've got N over 1, N air changes over 1 hour. But we really ought to think of it as in 1 hour, how many air changes are we getting? So let's say we wanted 6 air changes per hour. That's 1 air change in 10 minutes. But that's only, if we have mixed flow, then let's say we really remove 50% of the air in that first 10 minutes. And you're going to recognize this curve, right? Because anything that's 1 over N is going to have a curve like this shape right here. So at 20 minutes, we still have a little bit more. We have about 25% of the old stale air still in there. In fact, we don't really get to 95% reduction. We don't really get a full air change until more than an hour later. So depending on how much we're worried about an individual particle, how much we're worried about a contamination rate, how much contamination have we had, 6 air changes per hour might not be enough for us to clear a room in 1 hour. And then we need to think about the fact that we've put people into a room, and let's assume that someone, maybe two someones in that room are contagious and are shedding virus. They are more like a formaldehyde emitting material, right? If you put a material into a building that's made with formaldehyde, it's going to emit that volatile organic compound. And what IAQ experts have found, what a bunch of studies have shown, is that you're not going to ventilate your way out of something that is continually emitting, right? So with formaldehyde, for instance, when we get a decent air change rate, we can reduce the concentration a whole bunch. So it's really good. But after the kind of a half an air change per hour up to an air change per hour, there's very little improvement as we increase the rate of air change, because that constantly emitting formaldehyde, in this case, is repositioning materials in the space. And so when we think about actually having people in there, we're going to have to do more than just ventilate. Even though I just said that ventilation, dilution is the solution to pollution, that only goes so far. So one concept is the all fresh air, super clean building, right? And this would be to completely separate the exhaust and the supply airflows, to have no recirculating air at all. And in this case, we have displacement ventilation, right? We have all the air supplied in one place and extracted in another. And so that's going to actually, and by pulling it away from people, we're actually pulling the particles down and away rather than letting them mix and share with people. And this has some useful technologies, right? It's got an energy recovery coil. It's a pumped runaround loop, and we can talk about how efficient that is, which is to say not. But it can recover some of your energy. And we have all these filtration devices and so forth. So this is one concept. And maybe if you had a building capable of doing 100% outdoor air, you could revise your building so it could function like this and be ready for the next time you're putting large numbers of people into this building. So let's now talk about how we can apply this stuff kind of right away to situations we might face. So one of my favorite solutions takes this idea of high filtration surface area and low delta P and says, let's get, what would this be? 4 filters. These are HEPA filters or MERV 16 filters. Arrange 4 of them. So now you've got a lot of surface area and a lot of airflow range. And then you put a cheap box fan on it, tape it all together, put a piece of the cardboard from the box that the box fan came in at the bottom, and you now have an air purifier. This air purifier moves more air and is way cheaper than the air purifiers that you can buy at a store, right? This thing's going to cost you less than $100 to make, maybe about $100. And a really good air purifier is going to cost you several $100s, and have a lower clean air delivery rate. But if you are, and essentially the clean air delivery rate is going to be whatever the airflow of that fan is that you buy after it's had the resistance applied to it from all these things. So it's going to be slightly lower. But the filter that you chose is going to determine what material is being filtered out. So you want the highest MERV rating filter that you can get. If you're going to buy an air cleaner, which does work, right? And a commercial one may look nicer, be a little quieter. There's lots of good things for one that you can buy. You'll want to find the CADR, the clean air delivery rate for cigarette smoke, because it's often rated for different materials. You want the one for cigarette smoke, and that one will also cover you for viruses. So if you were to put people who are not in a pod together in a room, obviously the shorter the amount of time, the better. But while they're there, this is the technique I use to try to clean the air in addition to ventilation, right? Because we not only have the number of air turnovers that we can get, but we need to clean the air while it's in there so that that half-life rate of dilution doesn't have to work as hard, doesn't have to do as much of the job for us. For buildings that are, not homes, we can flush the buildings, making sure that we get a good 3 air changes at least, right? So really try to flush the building. And to try and save energy, we want to use an aggressive setback temperature, right? So when nobody's there, there's no reason to keep anyone comfortable. And if you have demand controlled ventilation, this is typical for schools or for universities. If you have demand controlled ventilation that's usually controlled by carbon dioxide, if you set the controls to pretty close to what we have as outdoor concentration of carbon dioxide, which I'm sorry to say is higher now than it was before. So around I said 415, I should probably say 425 now. So we're getting higher and higher concentrations because that's what we're doing. But if we use that, it's going to set it to pretty much demand outdoor air whenever anybody's in there breathing. Okay, multifamily apartments. So unlike single family apartments or housing, when you put a bunch of houses together into a single building, they often are actually pretty well connected, and this can cause contamination problems. So what we're going to want to do is compartmentalize the apartments, actually separate them so that they function as separate buildings. And we need to increase the outside air, and we need to block recirculation air if that's part of the design of those buildings. So compartmentalizing has an energy efficiency benefit because it basically reduces air exchange that's unintentional. And it has all those other problems. All these other measures, though, isolating infected people, closing off shared HVAC, which means providing electric resistance heating and maybe window air conditioning for people who otherwise would have those in connected systems, using negative pressure. So that means exhausting air that you've paid to heat or cool. All of that stuff is going to cost energy, but at least in this short term is probably worthwhile if you know that somebody's infected in one of these apartments. Common areas, you really need to limit access, increase ventilation, and add portable filtration like what we talked about. And we can see how this can actually function. So this is a study that's in the press right now. You'll notice it's in South Korea. You can't do a study like this in the United States very easily because we're so overwhelmed that we can't really do contact tracing. And you need to figure out who is sick and what apartment they're in before you can do a study where they showed that in these apartments with red on them, people got sick. And they're all connected to these vertical air ducts associated with fresh air and with the bathroom. And so what you can see is the stack effect is actually moving air from one apartment to the other. And in fact, their drawing that I copied, from the article, actually has it wrong because this is not really how the stack effect works. The stack effect is going to, if we have low temperature outside, if it's cold season, we're going to be sucking air in the bottom and blowing it out the top. So we're actually going to be moving from, say, 2F, we're going to move a virus from 2F up into 12F. When it's hot out, when it's in cooling conditions, it's going to move in the other direction. So we have, say, a virus in 12F, and we're going to actually drop it into 5F and 2F and so forth. But the basic idea that the stack effect plays a role does still make sense. So before we were worried about this, we were worried about stack effect. And so you can see if you have a big, tall building, right, there's somewhere is going to be a neutral pressure plane where essentially there's no pressure in or out. And it's that transition, and this is in a winter condition, we have upward moving stack effect. But so you're really drawing air in from below and pushing it up and supplying it from these other rooms into the building. If you've ever lived in an older apartment building and found that if you're on the top floor, you had to open your windows all the time to keep from overheating, even in the middle of winter, you know what the stack effect is doing. It's drawing heat from down below. A similar thing happens where you can have a high effectiveness of exhaust ventilation, say from a bathroom up on the top floor, where you're getting, I'm going to name a number, 200 CFM coming out of a bathroom in the top floor. And the bottom floor, you may actually be exhausting nothing. You're not able to get that draw out. And so that's the kind of balancing problem we have when we have connected vertical shafts. So compartmentalization takes the stack effect, whatever it is, whatever level of leakage is happening in the building, and isolates it for at least for each floor. So that prevents this transmission from floor to floor. And while we're at it, we should provide good ventilation, and we could provide balanced ventilation and heat recovery ventilation. Now, that's a lot of holes, and it's a little expensive, and there's filters that have to be changed by occupants, and all of those are things that modern building designers are having to consider. And so there are a bunch of workarounds that include partially isolated buildings where they have a common trunk line that goes to a common heat exchanger, but they've got individual supplies and returns. So there are lots of solutions to this. But the great news is if we can do all of this, this provides a permanent health and energy efficiency benefit and comfort benefit to everybody living in these multifamily homes, right? So in the longer term, compartmentalizing improves energy efficiency. Compartmentalizing the HVAC system improves energy efficiency and comfort. You now don't have to worry about isolating people in the future because they've been truly isolated. And then even the common areas, you have some things that you can do, which because of heat recovery, you're not paying an energy penalty for increased ventilation, at least not as much of a penalty. All right, so how might we deal with construction? Let's see. Oh, I'm using more time than I thought I was going to use. So I wanted to think about kind of interior work, especially in winter. So Habitat for Humanity consulted with me about what should we do to make sure that our volunteers who are doing construction don't get exposed to each other. And obviously there's masking, distance, all the stuff that we do. And we figured out there are certain jobs that you needed to do with two people. And drywall was the main challenge as well. It's a big, heavy thing. You want to hold it in place and fix it. And so we figured as if you can just get it attached with a respirator on and with a good ventilation going on, then an individual can come by. We need to avoid using circulation fans. So anytime air is blowing on a person, it can move those virus particles back up into the air. And what we want to do is actually let them fall. And then when we clean surfaces, remove them. But we can create a good deal of exhaust ventilation just by having box fans in windows. And yes, it's cold, and I'm going to get to that in a minute, but construction is often done in the cold. It's a different challenge when we're talking about painting or mudding and all those types of things that require certain temperatures to work, but that can also be done mostly by individuals. Dust management is different on construction sites. We don't want to use brooms that are going to push dust and virus back up into the air. Instead, we really need to focus on using vacuums that have HEPA filters, and you can put these HEPA filters on, they work, but you want to pre-filter them using a cyclone dust collector so that you're not filling up these expensive HEPA filters with large dust. You can use the same tool to create negative ventilation in really tight spaces, like if you're working to two people tacking up drywall in a closet, right? You got to put those people working really, really close together, but they can vacate that space, evacuate that space, actually using that HEPA filtered vacuum cleaner. And you get 11 ACH, right? So you get a really high rate of exhaust because it's such a small space. Okay, so this is where personalization, here's an example of personal comfort. You need manual dexterity, and I just made the place cold by sucking all the air out of it, right? If we go back to using incandescent light bulbs just for the winter, what we have is a heater close to where you're actually working. So that's pretty nice. For residential renovations, we still need to create a balanced ventilation. In this case, exhaust ventilation is not ideal because you don't want to draw in potentially virus particles from people in the residential, who are living in that residence. If you can't get them to leave and you're working in some part of their house, you want to isolate, but you still need balanced ventilation. Fortunately, you can get a pretty high rate of ventilation with fairly inexpensive fans. Okay, classrooms are the big challenge. So everybody probably remembers these heaters in their classrooms because almost every classroom in America uses this unit ventilator. And here's how the unit ventilator is supposed to work, right? It's got a coil that may have, let's say it's here in New England, it's got hot water that runs through it. And it's got a damper, and the damper can open to allow outside air in, and then that outside air is mixed with return air. So it's an air handling unit, right? It's exactly like the air handling unit that I showed on the top of a roof or in a big building. And it's moving that air over that heating coil, in this case, this mixed air, and blowing it into the room. And that's how they are supposed to function. But this is what they look like. And, so often they have filters. You're supposed to put a filter in, but those filters there's often a lot of bypass. And so not only are they ineffective, right? You're not able to exchange the heat that you want because you've got dust covering your heat exchange area. But if you're not filtering dust, you're not filtering virus. And so this is what these systems look like. And so as this past summer, we're trying to get schools ready for what we thought was going to be lots of in-person learning. There was an exploration of how much air can we actually deliver. And it turns out you could not get the rated amount of air through most of these unit ventilators because they were so clogged up. And often the air intakes were completely filled. It's maintenance, but person hours are expensive. And it's a lot of maintenance, a lot of things just not working. And so you have this problem of, do we fix it or do we just do without it? So in the case of one school in Northfield, we're actually going to do without it. We're going to clean the unit ventilators and turn them into simple fan coil units. And we're going to try and provide ventilation air using heat recovery. And so now, once you've separated those two functions, ventilation and heating, which could also be cooling, once you've separated them, now you can take the next step, which is their plan later, and actually change to air source heat pumps. And now you'd be able to get the school completely off of, or 90% off of fuel oil. And it's a long story about how we're going to get there, but the key choice is to realize that you need to separate ventilation from heating and cooling. So let's look at the economics of this for a moment. So normal classroom has about 3 air changes per hour, right? So let's say it's somewhere around here. We've got 55 heating degrees days, and we've got 8 hours per day, right? Because you're only ventilating when kids are in school. Well, with the efficiency of a boiler, all these things are factors that I'm not going to go into, except to calculate that with natural gas at $1.40 per therm, the cost right now without heat recovery is $166 per classroom, right? Which is not a lot of money, really. That's just the cost for heating the fresh air. If we have an HRV, which is 80% efficient, which is not the best one you can buy, but it's one we've got, and it's going to cost us $5,000 to install, our savings is pretty big, right? We're saving $133, but the payback period is still 37 years, right? It's not great. But if we have to run our heat run our ventilation for 2 hours before school and 2 hours afterwards, because that's what's recommended, and we have to run at 9 air changes per hour because we've got all these potentially polluting people. Well, now our cost, if let's say we have a unit ventilator and we haven't done heat recovery, our cost to operate that is now close to $700 just for ventilation. That's not looking at the electricity at all. So with an HRV installed, our savings are $560. Now we've got a payback period that's more reasonable for institutions. 8 or 9 years, they can handle that. And what they're getting out of it, of course, is fresh air. And what we've seen is that and this is just one example of a study that those students have taken BCT 150 will probably recognize, that when we give people a higher ventilation rate, if we really double the amount of fresh air that they get, we get huge jumps in cognitive performance. And if that's what school's really about, is learning and cognitive performance, then maybe this is a good investment in education, regardless of whether we have a pandemic next year or not. Let's pray not. So what do we take from this period as we try to operate in the pandemic? I think that, one, we should be ready for the next pandemic. I don't think we will be fooled into thinking it can't happen. We're going to hopefully maintain somewhat higher ventilation rates, even as, say, everyone's vaccinated, and we can go back down to something closer to the recommended code. But the big story, I think, is that as we increased our ventilation rates, we may realize that we should be separating our HVAC functions. So we should do ventilation with ventilation equipment. And we can do a whole lot. We can move less air, do less work if we provide our heating through mostly radiant heating. And if we want to do humidification, let's do humidification separately, whether it's as part of the ventilation equipment or as a standalone function. And also we can do sensible cooling with radiant cooling at much higher temperatures than we do when we're trying to do dehumidification. And dehumidification can be incorporated with ventilation, making for a much smaller system that's much more finely tuned to how we're actually doing things. And that means that we've got a whole lot less recirculating air. Essentially, we don't recirculate air. And so I think as we start to build more and more buildings or retrofit more and more buildings, realizing that we have to be capable of delivering high rates of ventilation, it will make more and more sense to separate all these HVAC functions. So I realize I droned on and on a bit, but I would be happy to discuss any of this, answer questions, and hear other people's ideas.
So we want to take some questions from the floor. We have a few minutes while Kath puts together the questions from chat.
Yes, I have, just so people know, I have no questions yet. And I will also invite people to ask questions directly if that's easier than typing them out, sending them to me. So don't be shy, ask away.
And I'm also looking at the everyone chat because, you know, I'm also a UMass professor, so I'm used to this now.
Right.
I have a question. how can we ensure with like future post-pandemic clean air and new ventilation systems for like lower income families and people who can't afford these new technologies?
Yeah, so I think that's a really good question. So in a sense, when we're thinking about residential buildings, right? So if it's safe, we have to think about single family low income housing, right? There's plenty of single family housing that's also low income. And in that case, we really don't need to provide the high ventilation rates. We still need fresh air. And it would be nice to get them heat recovery ventilation. But at a minimum, in many cases, the first thing is actually to tighten it up, to actually get them less fresh air, because right now their buildings may be too leaky at times when they don't want it to be leaky, and that causes building durability and health problems as well. So the ideal thing would be to connect those families with weatherization assistance, and possibly in Massachusetts with MassSave, where they can get air sealing done. And as part of that, either often they'll provide, at no cost to people through weatherization assistance, HRVs, so heat recovery ventilators, or this is not the preferred option, but it is more common, exhaust fans that run at a low rate 100% of the time. Basically, they'll take a bath fan and it'll run at 20 CFM or something like that all the time. So that's what's done and what is certainly still viable. When we're talking about multifamily low-income housing, Carl was just talking about this expensive project. I know of one in Northampton, for example, that's actually going to be passive house. So the great thing is that as basically the economics, the tax benefits, how people finance new low-income housing, it actually makes a lot of sense to build these things to a passive house standard, which means they're airtight, cost virtually nothing to heat and cool, and have as a absolute requirement a code level of heat recovery ventilation. So in those cases, it's actually kind of like those families are likely to get better than what a middle-class family that is at market rate housing is actually able to get a hold of. I don't know if that helps.
Yeah, no, definitely. Thank you.
One thing it points out the dollar, the dollar amounts in the last slide, though, points out even at $5,000 a classroom, the justification in turning it into a shorter payback is reasonable, but you still got to be able to afford that first cost. And we certainly can understand the different availability of funds in different school systems to be able to afford something like an intervention like that.
So I'll give you the example of Northfield. They just got a Green Communities grant to implement this. And the reason it works is because it enables them to do other things that save even more energy. So by separating out the ventilation, they're able to turn their unit ventilators into fan coil units. Because so much of that fan coil, that heating coil, is dedicated to heating up very cold outside air and delivering it as comfortable inside air, because there's so much more coil, you now have a coil size that's so large that you can use really low temperature water. And so once you can do that, then you can use an aggressive outdoor reset, which for those of you who know it, and the others, I guess I'll explain it if it's necessary. But basically, you can save a lot of energy by lowering the water temperature that your boiler has to make when it's not really, really cold outside. So they were actually able to get a payback period for the whole project that was well under 5 years.
So are those fan coil units, are those two pipe, or are they going to cool? Are they able to cool with them now also?
Those are two pipe. And in other schools, it might work to use them for cooling. You just have to switch from one to the other. You couldn't do it simultaneously, but schools don't do a whole lot of simultaneous. You just have to put a condensate pan and a way to get the condensate out. The problem is this school, you have no access to some of the pipes around the school, and you need to insulate them or you're going to condense water on the pipes and make a big mess. So it's not going to happen, that part.
Ben, I have a question for you. So having been in schools and big apartment buildings where the tenants don't have control over heat, I guess, but particularly schools, I've noticed that windows are often bolted closed, right? And so when you were talking about the possibility of separating or the benefit of separating ventilation from heating and cooling, does this mean we can start to see windows be open a little more frequently for the fresh air and air exchange? I guess what is the role of windows in this, in thinking through?
So
COVID.
the challenge is that you have a heating system that's sized, usually for a building with its windows closed, right? And now it's kind of not true with really old ones. In fact, the old heating systems were sized back in the 1918 pandemic. And we actually sized things for everyone has to have their window open all the time. So you need a giant steam heater to satisfy everything. So, but current sizing means that you would either have inadequate heating, you'd waste a lot of heat. But the reason people open and close windows is because it got stuffy or it got too hot. But if you have good control and you have good ventilation, it's not going to get stuffy and the temperature will always be comfortable. And people will open windows at exactly that time of year when you want to shut down the HRV, shut down the heating system, and enjoy the fresh air. It makes stuff work, and then people won't have to get around it.
Right.
So we have a good question that just showed up we can wrap this up, but it takes it to the future. And it's since air quality can be controlled with MERV, since building codes change with the times, do you think that the COVID-19 pandemic could influence the next set of building codes? It might change in addition to ventilation systems.
Yes and no. So I think that it is possible that there could be a change in ventilation, building codes related to ventilation systems, because ASHRAE is the organization that is referred to as the standard. And so in other words, the building code authorities, the IBS and all those kind of defer to ASHRAE on things like ventilation. What they tend not to defer to ASHRAE on is the energy efficiency side. And that's where the builders have basically been working pretty hard to make it so that the codes do not improve in terms of delivering better energy efficiency. So I think that it may turn out that they use the argument that we need more fresh air to say you can't require buildings to perform better. Yeah.
Well, as usual, a candid answer from Professor Weil. That's the way it is. This is what the community that you're moving off into, and you leave academia. So typically our presenter gets the famous BCT water bottle. Not the case this time. No budget constraints here, and Professor Weil's already got one, but certainly